People of the world, today we will continue discussing momentum transfer. But let me start by requesting you to hit the subscribe button. I will be very happy if you do that. I had already discussed to you about fluid flow, and in my last video, we talked about dimensional analysis. Okay, let us again play with the units. That's less stressful than the term dimensional analysis. Our target is to reduce the number of initial variables by grouping the variables into dimensionless parameters. And we have a more general approach to do this. We call that the Buckingham Method. According to this theorem, the number of independent dimensionless groups I used to describe a situation involving n variables is equal to n minus r, where r is the rank of the dimensional matrix of the variable. Suppose, suppose there are n variables. The functional relationships between the variables can be written as the function of q1, q2 until you end with qn, and that is equal to 0. The method involves choosing a number of the original variables to form what is called a recurring set. Any set of variables may be chosen with the following two provisions: that number one, each of the fundamentals must appear in at least one of the n variables. And number two, it must not be possible to form a dimensionless group from some or all of the variables within the recurring set. The dimensions of the physical quantities may be expressed in terms of fundamentals like mass, length, and time, and sometimes temperature and thermal energy. The table shows the important variables in momentum transfer. On the left side of the variables, on the left side are the variables. In the middle are the symbol of each variable that are generally recognizable by a chemical engineering student. And on the right side are the dimensions of each variable. On the other hand, this table shows the common dimensionless parameters in momentum transfer, like the Reynolds number, Euler's number, coefficient of skin friction, Froude number, Weber number, and Mach number. And by the way, this has already been shown to you in the previous video. Now let us look again into the situation and the problem I discussed to you in the previous video. We start with interpreting the situation in the figure. The relationship in the problem can therefore be expressed, as I said, change of P equals to the function of D, L, V, rho, and mu. Using the Buckingham method, we express the mathematical equations as a function of change of P, D, L, V, rho, and mu equals to 0. The number of independent dimensionless groups I equals to the 6 variables involved and 3 rank of the dimensional matrix, that is the mass, length, and time. Thus, 6 minus 3 equals 3 independent dimensionless groups. The recurring set must contain 3 variables that cannot be formed as dimensionless group. From the variables, since based on the problem, change of P is the dependent variable, it would be more appropriate to place it in only one group, obviously not in the recurring set. D and L cannot be combined with the recurring set because they can form a dimensional group. That is, if you divide L with D, both are in the units of length, hence dimensionless. You can only choose one, it's either D or an L for the recurring set. So, if we chose change of P, D, and L, and it's not an option. Likewise, when we have change of P, V, and rho as the recurring set, since when change of P is divided by V squared and rho, it results into a dimensionless group, the Euler's number. The most logical combination, therefore, is T, V, and rho as the recurring set, considering that it cannot form into a dimensionless group. Of course, because they form your recurring set, they will recur. That is, you will be seeing them in the dimensionless group. We take note that the dimensions for the three variables, T, V, and rho, must be expressed in terms of mass, length, and time. So we go back to the table and see that V is equals to L over T, and then density equals M over L cubed. We will then substitute these dimensions in the equation. First, if we have T equals L, logically L will be equivalent to T. Then, if the dimension from the table of V is D over T, then upon substitution of L equals T, we get V equals L over T. And we can arrange that as T equals L over V, or that will be dV raised to negative 1. Also, the dimension of density equals M over L cubed. We rearrange that upon substitution of T, we get M equals density rho times D cubed. Change of P, L, and mu therefore forms the dimensionless groups. Correspondingly, change of P will be for group 1 and L will be for group 2 and mu will be for group 3. Well, also that from the table, the pressure is M over LT cubed and length equals L and viscosity equals ML, M over LT. We'll then substitute these dimensions in the equation. For group 1, change of P, it has a dimension of ML raised to negative 1, T raised to negative 2. To make it dimensionless, we simply divide it with the dimension. Thus, you have change of P over ML raised to negative 1, T raised to negative 2. We can, of course, write this also as change of P M raised to negative 1, L raised to 2. Now, we have already determined that M is equals to density times D cubed, L equals D, T equals dV raised to negative 1. So we can now substitute the variables of M, L, and T on our written expression of change of P, M raised to negative 1, and times L times T raised to raised to positive 2. Thus, we are getting an expression of change of P times the quantity rho D cubed raised to negative 1 times again the quantity of T times the quantity of dV raised to negative 1 quantity raised to 2, which can be simplified. Thus, you have your change of P and you simplify density D cubed raised to negative 1 into density raised to negative 1 times D raised to negative 3. D does not need simplifying, and you just bring it down. And then we have also dv, quantity dv raised to negative 1, quantity raised to 2, which will now become d squared times v raised to negative 2. With d raised to negative 3, and you have a d raised to 1, d raised to positive 2. If we simplify this, you get a d raised to 0, and that would be equivalent to 1. The equation, therefore, can be further simplified into chains of p times density raised to negative 1 times v raised to negative 2. Finally, we have a change of p over density v squared. For group 2, L has dimension of the big L. To make it dimensionless, we simply divide it with its dimension, thus small l over the big L. We can, of course, write this also as the small l times l raised to negative 1. Recall again that we have already determined that L equals T. So we can now substitute the variables of L on our rewritten expression of small l times L raised to negative 1. And thus we get an expression of L, small l times big L raised to negative 1 is equivalent to small l times d raised to negative 1, or that's equivalent to just 1, L over d. For group 3, mu has a dimension of m l raised to negative 1, t raised to negative 1. To make it dimensionless, we simply divide it with its dimension. Thus, you have mu over m l raised to negative 1 t raised to negative 1, which can, of course, be written also as mu times m raised to negative 1 times l times t. Recall again that we have already determined that m equals density times d cubed, l equals d, t equals d times v raised to negative 1. So we can now substitute the variables of m, l, and t on our rewritten expression of mu times m raised to negative 1, l, t. Thus, we will be getting an expression of mu times density d raised to 3, and you have a quantity raised to negative 1. Then we multiply it by the t, and then by the quantity dv raised to negative 1, which can be simplified. Thus, the rho times d3, and this quantity is negative 1, can be written as the density raised to negative 1 times d raised to negative 3. D does not need simplifying again, so we just bring it down. And for dv raised to negative 1, it's now d times v raised to negative 1, which can be further simplified into mu times rho raised to negative 1, d raised to negative 1. Then we have a v raised to negative 1, or if we rearrange this equation, taking out all the negatives, you have a mu over density d times v. Now, we have already determined the mathematical expression of the dimensionless groups for change of p, l, and then also for mu. We can now substitute. The result, of course, is it is a function of the change of p over density v squared, and an l over d, and a mu over density dv equals to 0. Or we can have that as the function of L over D and density d times V over mu, and that will be equivalent to your change of P equals to density V squared. In the final equation shown, we have inverted mu over dV, over rho dV, arbitrarily to conform with the Reynolds number. Hence, we express it as density d times V over mu. So that ends our discussion on dimensionless, dimensional analysis. Thank you for watching the video.